This is a presentation of General Electric Medical Systems Institute.
I couldn't believe it. It happened so fast. I started to walk over with the wrench and it just ripped out of my hand. It flew into the magnet, smashed into the wall, and bounced back onto the magnet. Lucky no one got hurt. Yeah, that thing was really moving. And nobody else was in there, and I just didn't know the magnet was always on.
I'll never make that mistake again. Just before the scan was to start, I brought the patient in on the gurney. When I got within about 3 feet of the magnet, the oxygen bottle just slid right off the bottom rack and jumped up into the bore. It was terrifying. Well, thankfully, everyone's all right, but when I think what could have happened... From now on, I'll check everything with the hand magnet.
Today was the first time I'd ever cleaned in that room with the magnet. Nobody ever told me what could happen. Had my mop bucket over by the door when I started. Turned around, and a minute later, saw the thing moving by itself. Couldn't believe it. Then the bucket slammed into the magnet. Now, there was a problem. Just getting it off the magnet was a real job. Never again. Any new people who start here better learn what they can and can't do.
Magnetic resonance is a revolutionary technique which may prove to be as great a tool to medicine as the X-ray. Its expanded ability to see the invisible gives us new powers of diagnosis. MR is a complex and sophisticated diagnostic imaging device. But at its core is a simple and powerful force: magnetism. Magnetic force can't be seen, makes no sound, offers no warning at all that it's even there. But the MR system power is awesome. Up to 25,000 times the force of the Earth's magnetic field. And how strong is that? Compare it to the power of a crane magnet, which can lift up to 4 tons of iron and steel. The field of the MR system magnet is even stronger. This tremendous force is needed for the system to do its job of aligning hydrogen atom protons so imaging can take place. But despite its great power, the MR magnet functions like any magnet, large or small. For example, a bar magnet. Its magnetic field is revealed by iron filings. The filings align themselves along the magnetic field lines from one pole to the other. The same magnetic effect is produced by electric current flowing through coiled wire. When the electric current is increased, the magnetic force increases with it. The closer lines indicate a stronger field, and where the lines converge, the force is strongest. The MR system magnet requires a tremendous amount of electric current, up to 1,300 amps, or 13 times the current in an average household. That's why the conductor in the MR system is supercooled. This removes electrical resistance in the conductor, so there is no loss of current. The supercooled conductor also means no additional external power is needed to keep the current flowing within the magnet coil. Thus, the magnetic field is almost always present. So even though the system may not be in use, the powerful force is still there. The MR magnetic field shape is the same as that of a bar magnet, pulling with the greatest force where field lines converge. And as with any magnet, the closer you are, the greater the magnetic force. How strong is the force? how would it affect some of the tools and other objects that might be accidentally brought into an MR scan room? We've prepared a demonstration area at GE's MR manufacturing facility in Waukesha, Wisconsin. You will see some experiments and demonstrations which should never be attempted outside of this carefully controlled environment. The magnetic force on an object is a function of three factors: its mass, its distance from the magnet, and how it's oriented to the field lines. What will be the force exerted on a 2-pound pipe wrench? Securing one end of a line to the wrench and the other to a strain gauge and winch allows us to measure both the force and distance from the magnet bore. At a distance of 2.5 feet, the gauge reads 3.7 pounds. Reduce that to 2 feet, and the force rises to 10.8 pounds. Now, as we get closer, the force will increase dramatically. This graph plots force against distance and shows that at close range, the magnetic force doubles or triples with just a few inches movement toward the magnet. And finally, at the magnet, this 2-pound wrench is pulled with a force of more than 50 pounds. If the wrench should slip at this point, how fast would it fly into the magnet? For this experiment, we'll take a rubber ball filled with steel shot and toss it into the magnet. A radar gun will indicate the speed. In these tests, we measured speeds of 20 miles per hour or more. But more important is the rapid acceleration and unpredictable direction. The ball can take any number of routes as it flies into the magnet bore. Imagine the damage that could happen if this were a wrench, oxygen bottle, or other sharp or heavy object bouncing around like this. And what would be the impact of a wrench accelerating into the magnet as the pulling force reaches 50 pounds or more? These demonstrations, which should never be attempted by anyone outside of this controlled environment, show the overwhelming power of the MR system magnet and the sudden violence that can result from carelessness or lack of knowledge. To guard against mistakes in the magnetic resonance environment, make sure that everyone who works with or near the system is continually reminded of the guidelines suggested by the manufacturer.
The MR safety guidelines is required reading at our facility. All the sections are important, but a number of points have been especially helpful to us. For example, the use of warning signs. We've placed them at several locations near the scan room and control room. We also use a hand magnet to check wheelchairs, gurneys, oxygen bottles, and other objects that might be magnetic. If they are, then of course they should not be brought into the scan room at all. The same is true of tools or any other magnetic objects. They should never be brought into the scan room at any time because, of course, the magnetic field is always present. Patients, too, should be checked. There are some who should never enter the scan room and who cannot be diagnosed using MR. Those with pacemakers would be in great danger of cardiac arrest in a strong magnetic field. And those with implants, such as steel pins or with artificial limbs, could also be in some danger while in the strong magnetic field. What should the procedure be if someone is hurt in a magnet-related accident? Again, the guidelines are very helpful in pointing out some basic steps. 1. Get the injured person outside the field and notify a doctor. 2. If smoke comes from the magnet, or if the oxygen alarm sounds, evacuate the area. And 3. Notify your service engineer to remove any metal object that may still be in the field. And if someone should be trapped against the magnet, the guidelines state, it's most important to notify the system operator, a physician, or the service engineer. Because if the decision is needed to remove the magnetic field, you must have one of these key people involved. Your institution may wish to develop its own procedures for dealing with emergencies, if they aren't already in place, and for dealing with the other suggestions for safety in the magnetic resonance environment.
Magnetic resonance has proven to be a powerful imaging tool, and its potential for diagnosis is just starting to be realized. So, in the future, you will become even more familiar with the MR system. As you do, beware of taking MR and its power for granted. Magnetic force acts suddenly. It will not forgive a careless mistake. The force cannot be seen or heard, and may not even be felt until it's too late. Remember, too, this sudden, invisible force is always present. Take every precaution at all times.
Now I know the magnet is always on. You can bet I'll never make a mistake like this again.
And like I said, any new people start here gotta learn what they can and can't do.